Hey everybody, so today we're going to talk about moment of inertia. So moment of inertia can also be thought of or referred to as rotational inertia. So let's think about what we know about inertia. So mass, right, is a measure of an object's linear inertia. So if I just have like this rock, then its mass is a measure of its linear inertia. And so very often, if I told you, okay, which weighs more, between these two pens, you might put them in your hand and you might naturally kind of do this motion, right? To kind of feel the mass of something, to feel its weight. So why are you doing that? Why can't you just hold them steady? Why do you notice the mass more when you move your hands up and down? So the reason for that is because when you move your hands up and down, you're actually changing its velocity and getting an acceleration, right? Up and then down and up and down. And so it's actually at those turnaround parts where it has the largest acceleration, the largest change in velocity, that you notice its inertia. How hard is it to change its velocity? That's literally what inertia is. So a linear inertia is how hard is it to change a linear inertia. So conceptually, that's what mass is, right? How hard is it to push something? How hard is it to change its linear velocity? Sorry, I had said inertia before. How hard is it to change its linear velocity? So rotational inertia is the same idea, but in rotational world. Rotational inertia is how hard is it to get something to rotate? How hard is it to get something to spin, to change its angular velocity? So that would be like this motion to compare these two. And I actually find that this little yellow guy is way easier to get to rotate than this one. And so that's that sort of motion. How hard is it to get to rotate? So this is linear inertia, kind of changing the linear velocity, changing the angular velocity. That's rotational inertia. And it's very important to have this conceptual understanding of rotational inertia as we go through. Now, we don't really call it rotational inertia. We call it moment of inertia. So you just kind of get used to hearing moment of inertia, but you think rotational inertia. So some things you can do at home. This was a very hands-on, in-person kind of part of our class. And so some things you can do at home to kind of help your understanding of this is just find, a long pen. If you have one, even better. If you have a long stick, you can kind of take one off of a tree, or I have my son's drumstick here. He is not, he's just for fun. He got it when he was 3. Was not the best choice as parents. So anyway, he has fun with it, but I have his drumstick right now, luckily. And I can sit there and I can think, okay, I'm gonna rotate this, right? Kind of like this. How hard is it to get to spin? Kind of notice things. We move things around a lot. We don't rotate a lot of things in this way. Also notice that if I pivot it at this end, right, and I try to rotate it kind of along a different pivot, that's different than if I try to pivot it this way. Or if I rotate it around its skinny end that way. So this one object actually depends, how its rotational inertia will depend on which axis it's pivoted on. And then even more interesting, you can get like an object, if you have Play-Doh, I surprisingly couldn't find any. I'm gonna just like try to tape this rock to this drumstick and then just basically try to have it so that a hammer could also work. But I kind of wanted to show you all the different things you might do depending on what you have accessible at home. So you kind of get on, this object onto your long stick. So it's heavy on one end and light on the other. And then what you're going to do is you're going to try to rotate it around the end that has the heavy thing. And you'll notice it's very easy to rotate it here. But if I try to rotate it this way, then what I find is that's much harder. And I'm pivoting it then away from the mass. So the complication with moment of inertia, how hard is it to change an angular velocity, is that it's not just how heavy something is, how much mass is there, because yes, that makes it harder. Heavier things are hard to spin, but where the mass is relative to the pivot. And what you should find, and what I encourage you to kind of walk around your house and just start spinning things, what you should recognize is that things that have the mass closer to the axis of rotation, so in this case, say the rock, this is very easy to rotate. But if I take that same object and I try to rotate it with the mass far from the axis, say in this way, right? That's very hard to rotate. This is easy, the mass is close to the axis, this is hard. Another example is the ice skaters. Ice skaters spin really much more slowly when their arms are out. That'd be mass far from your axis. And you move your arms in, and then you spin really fast. Okay, so let's go ahead, and I'm going to screen share, and then we're going to be able to see how some of this works out in our notes. And then later in this module, you'll learn how to actually calculate moment of inertia. But the conceptual understanding is really critical. You never really want to separate yourself from a conceptual understanding of the quantities that you're calculating. It really needs to be ingrained in order to truly grasp physics. So conceptual understanding of moment of inertia. What I had just said was that it's basically Newton's first law, but for rotation, which is that the moment of inertia is a measure of an object's rotational inertia. Just like mass was a measure of linear inertia. Right? So just like mass was a measure of linear inertia. So really what it is moment of inertia, and we often just write this as MOI. So moment of inertia is a measure of an object's resistance to change in its angular velocity. So it's a measure of an object's resistance to change in an angular velocity. So how hard is it to get something to rotate? And so the key takeaway is that a higher moment of inertia means that it's going to be harder to rotate, more inertia, and therefore harder to rotate. So at that point, you know, again, I really encourage you to go actually feel things yourself. Next time you have to, you know, cook or eat, like pick up a spoon and start, you know, trying to make it rotate, you know, spin things around on a table, things like that. Really just get a feel for this rotational motion and the different inertia that objects have depending on which axis you pick, right? So there's a couple kind of key takeaways from the experiences that you can have when you try to go around rotating things. The first thing is what I was talking about with the mass distribution, is that the moment of inertia depends on not just the mass. Yes, heavy things are harder to get to rotate, but also on where that mass is, the mass distribution. Where is the mass relative to the axis? Like if you pivot or hinge something, in this case, all of my cases, I'm just using my fingers, right, as the fixed point that it's rotating around. And specifically what you should see is that the closer the mass is to the axis, then the easier it is to rotate. So something like a long bar, and then let's say it's rotating around its center. If you have two masses and then you can move them, sort of like a barbell or something, this top scenario would be easier to rotate than if I put these little masses way out on the ends. So this would have a lower moment of inertia because the mass is closer to the axis. So that's going to make it a little bit trickier to calculate, right? With mass, it just is a property of an object, and we would just sort of give you the mass or find the mass of an object. Here, we're going to find that we actually have to take into account the density and the mass distribution of an object in order, and the relative, distance to the pivot in order to actually calculate these moment of inertia quantities. The other thing is, because it depends on the mass distribution from the axis, that the moment of inertia is not fixed for a given object. It depends on the axis. So the moment of inertia depends on the axis of rotation. So one object can have like an infinite number of axes of rotation, and therefore an infinite number of moment of inertias. So a given object has an infinite number of possible axes, so it also has an infinite number of moment of inertias. And that's okay. In a problem, you would be given the axis. You will be told the axis in a problem, or else you can't solve it and you can't analyze the motion. And then the last thing I'm going to just say in this conceptual understanding is, because it depends on our mass and our mass distribution, I'm going to just kind of give a sneak peek into where our formulas and our calculations will lead us by talking about the units. So the units of moment of inertia are going to be kilograms, which makes sense, that's the mass, times meters squared, where it's going to turn out that that's going to be the distance of little mass pieces from the axis of rotation. So it depends on sort of a length scale and on mass. And just so you're comfortable getting used to the symbol for it, moment of inertia, they kind of ran out, they can't use M, lots of things are already taken. It's just capital I. So that's what the symbol for moment of inertia is. Okay, let me know if you have any questions.